Hi friends, so through this tutorial I would like to cover ANOVA, one-way and two-way ANOVA and MANOVA. Okay, I would like to go through all of these statistical tests, would explain you assumptions, the meaning, when to use them, and then we'll do practical session in R. Okay, so let's start. The prerequisites for these sessions are the audience should have a little bit knowledge of t-test. They need to know the basic commands in R and R Studio and the basic knowledge of descriptive statistics like what is mean, median, mode, etc. Okay, so what is ANOVA and how is it different from t-test? So one-way ANOVA is an extension of independent samples t-test for comparing the means in a situation where there are more than two groups. This is the simplest case of ANOVA test where the data are organized into several groups according to only one single grouping variable, also called a factor variable. Other synonyms are one-way ANOVA, one-factor ANOVA, and between subject ANOVA. There is a thin line of demarcation amidst t-test and ANOVA. That is, when the population means of only two groups is to be compared, then t-test is used. But when the means of more than two groups are to be compared, ANOVA is preferred. So let me show you a simple file to explain this. So let's see, we have a variable fertilizer which has various types from A, B, C, D to E, and then the yield. Yield may be in whichever unit. I'm not going to bother about the units, but let's say unit is a continuous variable. So for specific fertilizer we have a yield mentioned here. Okay, so fertilizer is a factor variable and it has various levels. In this case there are 5 levels or factors of fertilizer factor variable. When we say factor variable, it is a categorical variable and yield is a continuous variable. And in this whole case, fertilizer is a independent variable which may vary from A to E, while yield is a dependent variable, or we can say dependent continuous variable. If the fertilizer had only two categories, let's say A and B, so we would run t-test in that case. But because it has more than two categories, so we would run ANOVA in this case. This is how ANOVA differs from t-test. Okay. So let's move to the assumptions. So what are the various assumptions for ANOVA? Independence of observations. Each subject should belong to only one group. There is no relationship between the observations in each group. This is quite obvious assumption. No significant outliers in any cell of the design. So outliers in data should not be present. What are outliers? That I'll explain in next slide. Normality. The data for each design cell should be approximately normally distributed. Okay. Homogeneity of variances. The variance of the outcome variable should be equal in every cell of the design. Okay. So that means now we have some observations for C, some observations for A, and same for other categories of fertilizer. Now if you want to see, for example, for C we have something like 14, 10, and here maybe for A we have 5, 9. So in these cases the variance here for these observations and variance here, and similarly for other categories, should be equal. That is the meaning of this assumption. Okay, and same way when we say about the normality of the data, so for each category the data or the observations should be normally distributed. Okay, so what is an outlier? Objectively we can define them as values above quartile 3 plus 1.5 into interquartile range or below, and the same quartile 1 minus 1.5 into interquartile range are considered as outliers. So I'm not going to explain what is quartile range, but this is the definition of outliers. You can further surf it on internet. So this is how the outliers are detected in the data. Okay, we can use box plots as well for the same. Another thing that we would be using in this practical example is a library dplyr in R. So in R, there are various libraries and packages that we can load, and through these libraries, we can use various functions to work with our data. You know, we have data frame in R. So in data frame, if you want to select some columns, filter some rows, arrange, mutate, summarize, you can see the meaning on the right side in the form of description. Okay, these are the meanings of various commands mentioned on the left, and these commands can be used to work and play with the data in data frame. Okay, this we would be using in our practical example. Okay, so this is all about ANOVA that I wanted to cover. Now let's move to two-way ANOVA. So what is two-way ANOVA? A two-way ANOVA test adds another group variable to the formula. It is identical to one-way ANOVA test, though the formula changes slightly. Okay, so y is equal to x1 plus x2, y is quantitative, while x1 and x2 are categorical variable. Let me again show you a file or data where I can explain this in a better way. So if you see in this file, we have yield, fertilizer, and then soil quality as well. Okay, now let's compare it with the earlier example that I showed you. Earlier we had just yield and fertilizer. Fertilizer had various categories and yield was a continuous variable. But let's say if we have two categorical variables or factor variables, so in this case it has 5 categories, 5 labels. Here it is 3 label factor variable, soil. These both are independent variable, and we are trying to find out the yield where category is, let's say, C, and the soil is high. And does this yield value depend upon soil or fertilizer significantly? Or we can define null hypothesis as there is no significant impact of fertilizer or soil on yield. Okay, so I explain this null hypothesis in a very layman terms. Statistically, what we write in the test that I'll show you in practical. Okay, so here is the difference between one-way and two-way ANOVA. The major difference is in the number of independent variables. Rest is almost the same. So let's review the assumptions. These are almost the same as the previous assumptions for one-way ANOVA, and we'll see how some of the these are validated in R. So these are the exact statistical hypotheses that we create in two-way ANOVA. Okay, null hypothesis for each of the set are given below. Population mean of first factor are equal. This is like one-way ANOVA for row factor. Population means of the second factor are equal. This is like one-way ANOVA for the column factor. There is no interaction between two factors. This is similar to performing a test of independence with contingency tables. So let me show you a file we would use for MANOVA. So for here, if you see, I am taking a independent variable as fertilizer, again various categories. Now for these fertilizer, what would be the yield and what would be the water requirement, okay, for irrigation. I hope you are getting it. So there are two dependent variables, both are continuous. So we would like to see, because maybe for each fertilizer would result into different yield, but they may require different amount of water as well. So there are two dependent variables. Now when we run MANOVA, it may be the case that we'll come to know that fertilizer has a significant impact on water, fertilizer has a significant impact on yield. Which categories have a significant impact on yield, that we would need to run ANOVA between fertilizer and yield. And same way, if we want to know which fertilizer categories have a significant impact on water, we would need to run another ANOVA in R. Whatever output that we get from MANOVA, we cannot run a post hoc or 2K HSD test on the output of MANOVA. That's what we are trying to explain here. Okay, I hope I was able to make things clear on what kind of variables are used and what is the analysis that would be going to do with various combination of dependent and independent variables. Okay, and to summarize, I just want to show you one more slide where you can see the combination of various dependent and independent variable. What are the various labels or factors or groups in the factor variables, and what kind of test that would be helpful for our analysis. Okay, so if you can just go through it. Factor variable is one which may have two labels or groups, and then one dependent continuous variable, it would be t-test. Now you can see further what kind of tests are required and or would be applicable based on this information in the slide. Okay, so that's all I have in theory. Let's jump to the practical part in R.